Hi, last lesson we were looking at how carbon dioxide has, through geological time, had an effect on temperatures. And the amount of carbon dioxide in the atmosphere we can see has changed over time. Ice cores give us that information. Now, this is tied up with an idea you may have come across before uh, in school called the carbon cycle. How carbon, much like water, moves through different parts of the natural environment, uh, staying in some places for a while, moving through other places, um, in this cyclic pattern. I want us to explore this, but in terms of the geological part of the carbon cycle. This diagram that's in your books shows perhaps the more geological parts of the cycle. So we're not really worried here too much about things like plants uh, and animals and things like that, which are sort of temporary stores of carbon. What we're looking at here is on a bigger scale, looking at how geological processes actually um, move carbon around different parts of the environment. Now, to study this, we can think about the carbon cycle as what we call a system. Now, a system is thinking about uh, any set of processes as a series, firstly, of inputs. So this is where the thing we're studying is being put into uh, this cycle, where it comes from somewhere else and gets put into the thing we're looking at. Outputs, where the thing we're studying at, in this case carbon, is taken out of um, the area that we're looking at. Transfers, which is where um, the carbon or the whatever we're looking at is moved from one place to another, and finally stores, where um, the carbon may stay for a while. Now, what I'd like you to do is have a go at question 6. So this involves trying to identify on this diagram um, where we see the different inputs, outputs, transfers, and stores from the atmospheric part of the cycle. So we're thinking about this just in terms of the atmosphere. So where does carbon get put into the atmosphere? Where is it taken out of the atmosphere? How's it transferred within the atmosphere? And where might it be stored in the atmosphere? Use a colour key to highlight the different labels on this diagram and see what you can come up with. Okay, so if we press pause now and have a go at question 6. Okay then, let's have a look at some answers. So this is our diagram of the carbon cycle. Our inputs are clearly the volcanic gases that are coming out from mid-ocean ridges, volcanoes at subduction zones. But the one that a lot of people don't recognise or often forget is the carbon dioxide that comes from chemical weathering, released when rocks get weathered. That can, certainly at particular points of geological history, be a significant input of carbon dioxide into the atmosphere. For outputs, it's where rocks get deposited. Rocks will act as pretty much permanent stores of carbon. Limestones, in particular, if you think of shell material or chemical limestone that gets deposited in in the oceans, uh, that will contain significant amounts of carbon dioxide. Equally, any carbon materials that get subducted um, will take carbon out of this active carbon cycle. Transfers, the carbon will clearly move around in the atmosphere, but also dissolved in water as it runs into the sea. And really, on this scale, when for the atmosphere, we're not really talking much in the way of stores, other than the atmosphere itself. So, as we said, the removal of carbon from the atmosphere is all about deposition of these carbon-rich rocks, coal, oil shales, limestones that we talked about in theme 4. You can even argue diamonds are well, diamonds I suppose are going to be the most permanent store of carbon in the geological carbon cycle. Where this carbon comes from, then we've got the weathering of rocks, eruption of volcanoes, and crucially and increasingly the burning of fossil fuels. And it's that I want to think about next. Another one to consider as well is making cement. To make cement, we heat limestone up, we drive carbon dioxide out of it to leave calcium oxide. Cement can be a huge source of carbon dioxide in the atmosphere. Anyway, let's consider this fossil fuel thing. These are human impacts, where we actually are adding additional carbon dioxide into the atmosphere. These have been discussed, I'm sure, many times throughout your school career. Now, there are misconceptions about this. This guy, Nathan Gill, was a member of the Senedd, and in 2015 was trying to debunk the idea of human-made climate change, saying it was ridiculous to think that humans could change the climate. A volcanic eruption will produce far more CO2 than man has ever been able to do in the short time since the Industrial Revolution. Okay. What I'd like you to do is prove how wrong Nathan Gill was. I want us to actually look at the data for this. This is a measure of different sources of carbon gases into the atmosphere, looking at natural and human. Can you work out just how wrong he was? How much bigger is the annual emissions of carbon gases from humans compared to volcanoes? As well as that, we can also have a look at this. This is looking at some of the biggest eruptions of the last 50, 60 years or so. This is the blue line here shows the input of carbon gases from volcanoes, and in particular the effect of these big eruptions. The red line is the CO2 that's measured at Mauna Loa. What effect have they had? So, press pause now, have a go at question 7, see what you come up with.